as function of position, y-axis, and time, x-axis. So, in case of the acetic acid, original excitation always goes to perovskite. So you see this alternating blue and orange, which means the initial excitation stays on on perovskite. Orange means lead 5s orbital, and blue would be bromine, whatever, P6P, whatever is available there. And as time passes by, both electron and hole do migrate to titanium dioxide. So there is no charge transfer. Well, there is one very short transient charge transfer. By the way, it is similar to what Dan computed for your recent work. So, transient short period charge transfer, and then later lowest excitation, both blue hole and orange electrons stay on the acceptor. So final state is neutral. But if we allow this structural change by replacing isopropanol with hydroxyl, we start on both electron and hole originally on titanium dioxide, and then hole stays on the slab on titanium dioxide, but electron does transfer to the hole stays on perovskite slab, and electron jumps to titanium dioxide. So just a little chemical tweaking of the linker makes drastic change in the quality. Yes?
Is the color scheme same in the both figure?
No. No.
But in the bar by the picture image, their color scheme is.
This color scheme is a little better. Ideally, the green color in the middle of the rainbow progression should correspond to neutral. But
in the bar, the color bar is showing the same bar. Yeah.
No, but that's from like -7 to like 20.
And that one?
That one we can't really see, but it's much smaller.
This one is to be correct.
But I have a question. So it appears from the system to your dynamics that the whole, I think, the yellow goes to the hydroxide groups on the titanium dioxide quantum dot, not to the quantum dot itself.
No, if we align, it would be more like this titanium and oxygen. So there is no substantial density on hydroxide. It's more like mediator. See, those are layers of perovskite, and this would match more to this titanium and oxygens.
So is there a reason why they stayed on the near atoms instead of going throughout the entire?
Yes. System is polarized, and electron and hole attract each other.
They're bound in that case still?
Well, in this methodology, we do not have excitons. We do not compute how they are bound, but they should be. Good eye. And now it's time for the.
What's going on?
Oh, let me answer your question with a movie. Movie number 3 that I always wanted to show. So it is a favorable configuration.
Is it also from London?
He contributed substantially. So you see, originally it was yellow and
I didn't see the movie. Where is the movie?
It's
no colors.
It's very slow. See, it develops here.
I don't.
You don't see the
Oh, it's
yellow?
growing.
Yeah, it's growing color.
The movie is not. Be patient.
That's it?
That's it. It's not very dynamic, but it's of extremely high scientific value.
That's indicating the
Makes me feel better.
If you are not, if we are not so patient, we can just do it like.
Oh, this is better. At least something happening.
It's the log of time.
Yeah,
The
time is
movie
log
in
in
linear
log
time, right?
It's not linear time.
The movie is in log time too?
Yes. So
Probably take out several steps. You should go with the larger steps.
no, then it is very choppy. So, see, originally there is very small orange density on titanium. Titanium is these blue atoms.
What is in the bracket T1127?
So there is on bromine and
X-axis.
lead. And then, Levi, here is your hydroxide. So there is both electron and hole in the hydroxide. And then it substantially grows the yellow electron density on titanium 3D orbitals. See this like 4-petal structure.
So then why is it so intense on that titanium compared to the others?
Is it
Because we have
And again, hole is on titanium, right?
no, wait.
Electron.
Wait, electron, yes. Don't you know that electrons are yellow?
So what is
I'm
that
kidding.
in the yellow circle?
Huh?
What is this atom in the yellow circle?
Well, this is, well, color codes do not correspond in this image, but these blue atoms are titanium. This is not the whole structure, but it's only one slice across the middle of the structure. Otherwise, if one adds together and integrate it, it becomes uncomprehensive. And the relative density on titanium is much higher than the relative density, let's say, on bromines, because there are a couple of dozen of bromines and only like 6 titanium. So if we equally distribute equal amount of charge on bromines and titanium, relative amount on titanium will be higher, right?
Your titanium is just in one space, and bromines are
Right,
all over the
right.
entire cell.
Right.
So why not in the oxygen then?
Why not in oxygen?
In titanium oxide, there are oxygen.
Bromine is more aggressive. Not,
Oh,
why
titanium and oxygen?
why here not oxygen?
Yeah.
Good question, and the answer does exist. So, if you consider
Because the age of the conduction band is originating from titanium, not from oxygen, right?
yes,
Yeah.
so if you do have only titanium dioxide in your simulation cell, your conduction band is composed of titanium 3D, and valence band is composed of oxygen 2p. So there is, if you do pro current PDOS, there will be no oxygen-related orbitals in the conduction band.
Yeah.
So it was 3 movies, 1 left. I don't know about you, I'm already tired. I need to shorten it substantially.
Stop.
No.
Take a break. Return back next week.
No, next week to UND.
Yeah, everyone comes to UND to listen to you. No?
Ah. I can take 3 people in the car, but not everyone. Only maybe a pilot.
Is it 3 including me?
Well, we can put someone in the trunk.
No, you can put someone in the middle, in the back middle.
Okay, 4.
Oh,
So it's methods that probably should be sometimes at the beginning. So second order perturbation in respect to electron-ion interaction. Couplings are going from the non-adiabatic couplings along on the flight trajectory.